One great thing about researching the Milky Way is that we are actually living in it, meaning we can see the galaxy all the way down to the stars and gas within it that make up the galaxy, allowing us for a really precise view that we do not get with any other galaxy. The bad news is that, well, also that we're living in it. Welcome back to Space with SETI, the place where we talk about all things astrophysics related. I'm SETI, a PhD student studying the Milky Way, and today we're going to be talking about my own research. If you're into all things space and astronomy related, then this channel is for you and I recommend you subscribe. So what is my research on specifically? Well, the Milky Way, among many, if not most, spiral galaxies nearby, have warps in their disk. A spiral galaxy like the Milky Way will typically have three components that we focus on. You've got the bulge near the centre of the galaxy, the spirals, which are part of the main disk, and then also the halo, which is where most of the mass is concentrated within. However, when it comes to all these pretty pictures that we see from Hubble's deep sky imagery and just general astrophotography, it's the bulge in the disk that we observe. Now, while I focus on the disk specifically, within the disk there are two main parts, the stars and the gas. The gas can collapse and form stars and stellar clusters, and then those stars, when they're ready to, of course, die, they replenish the gas, and also explosions such as with supernovae or even planetary nebulae. When they form, they also shape and distribute the gas differently. So stars and gas are very heavily associated with each other. They share a common guiding force, which is gravity, but also the gas will have a lot of things like fluid dynamics, pressure, all of these other things to consider, whereas stars are effectively collisionless. Now back to the warp. Surveys that use young stars such as Cepheids are quite useful because they preserve the warp signature pretty well because they haven't had much time to travel from their birthplace. As for the shape of the warp, our current view is that it mostly takes on an S-bend, or even better yet, an integral shape, with a couple caveats. Now, the warp in the Milky Way starts within the intermediate radii of the disk, so this will be about between 9 to 11 kiloparsecs, or that will be around about 20 to 40 light years from the centre of the Milky Way. For context, the disk, although it's very difficult to, get an estimate for the edge of the disk, it's roughly around about 18 to 20 kiloparsecs long in radius, and then the sun is about 8.2 kiloparsecs from the centre of the galaxy. But why is our galaxy warping? Well, one of our main suspects is a companion galaxy called the Sagittarius Dwarf Spheroidal Galaxy, or I'll just call it Sagittarius for short. This is a really close by neighbouring galaxy which we know is currently interacting with the Milky Way and being pulled apart by it. Some of its stars have probably already assimilated into the disk, and some of them have been stretched out into a tidal stream which is called the Sagittarius stream. It is so small and so faint and dilapidated now that we don't actually have any good pictures of it at the moment. And while we know that it is definitely interacting with the Milky Way, the question really is that enough to cause the warp that we see today? Other ideas are that it is the LMC that is the dominant cause of the warp, which is also quite plausible. A mix between Sagittarius and the LMC, and this is expected to, well, each of them will excite different modes within the disk, which I won't get into for today because it gets quite complex, but this theory is one that I'm personally leaning more towards. And the other idea is that it might be small fluctuations within the dark matter halo. That is a lot that I have thrown at you, so we'll just recap. The Milky Way has a warp, which is roughly an S shape or an integral shape. The disk is fairly flat up until about 9 to 11 kiloparsecs, where then it starts to warp either up or down depending on the side, and it reaches a max of around about 1 kiloparsec for stars, a little bit more for gas, and plus minus a bit depending on which side you're on. The main cause is still quite unknown, but we suspect it is probably a companion galaxy like the Sagittarius or the LMC, or both. But there's a lot of grey area that stars and stellar surveys alone can't fix and help us with. Firstly, the further out we look, the more noise we get in our data, meaning the signal to noise ratio dips down, which can make conclusions quite difficult to make, basically. And this affects mostly the outermost regions of the disk, so really far out the edges of the disk, but also the central regions as well. So it's very difficult to know whether after it reaches that peak, does it flatten out, does it flare, does it dip back down and corrugate? It's just very difficult to know. Second of all, we also have the fact that right in the centre of the galaxy there is the supermassive black hole and the bulge as well to consider. And this blocks out quite a huge portion of the stars within the galaxy, and it blocks out one side of the galaxy. This is where simulations can come in handy. You can simulate a galaxy and run it for billions of years while actually just running it for a few weeks or months on a supercomputer. Also, your stars and your data is, virtually error-free, which can actually be useful in simulating errors and trying to understand how they will work and match them up to actual observations. That can be really useful. And thirdly, you can change different things about your galaxy and see how that affects things over the course of a few billion years. So I focused on mostly just an isolated Sagittarius interaction with the Milky Way, and the main question I wanted to ask was, given an impulsive, close-by impact with a satellite galaxy, how does the mass of that satellite affect the evolution of the Milky Way over time? To answer this, I need to set up my simulation. Now, I did not create all of this from scratch. If I had the tools to do that, I would have already got my PhD. But anyways, to set things up, firstly, I chose to only look at stars and make my model effectively collisionless. I used 10 million stars in total, which were spread out among 3 components within the galaxy. That is the bulge, which I modelled using a Hernquist sphere, a quasi-isothermal stellar disk, and then also a Navarro-Frank-White halo, which is where the majority of the mass within the Milky Way was, which closely reflects real-life estimates for the mass of the 3 components. Basically, I tried to set up my Milky Way so that it is as close to the Milky Way as possible. As for the impacting galaxies, so Sagittarius in this case, I modelled it using a sync particle, so that is a single particle which is really, really heavy. Basically, I just wanted to see how the disk evolves following a very impulsive interaction going straight through the disk and out. I didn't want to confuse any of the disk response with having stars intermingling and tidal streams or whatnot. I kind of just want to see the effects of the impact alone. So in total, I ran 4 simulations, so the Milky Way setup is going to be exactly the same throughout all 4. The only difference is I am changing the mass of Sagittarius. For my first one, I used as a control, so there is no Sagittarius mass. For the the second one, my small simulation, I used a mass of around about 1 × 10 to the 10 solar masses for Sagittarius. For my medium sim, it was 2 × 10 to the 10, and then for my large sim, it was 4 × 10 to the 10. These are all within ranges that we estimate the original Sagittarius mass to have been, prior to all the impacts and having all of its stars get pulled away into the Milky Way. A lot of this setup is actually thanks to Joss Bland-Hawthorn and Thor Tepper-Garcia. I'll link down to Thor's website if you want to have a look at all of their work. It's really amazing. So all that's left to do is to let these simulations run and collect 5 billion years worth of data. So I've made a few videos showing you what's happening. I'll start off with the small sim, move over to the medium sim, the large sim, and then the control simulation as well. So on the left-hand side of this, we're first focusing on the small simulation. We've got the bird's eye view, so top-down view of the galaxy, of the disk specifically, and then on the right we've got the side view. We can see that there is quite a lot of warping that happens right off the bat, and then there's a lot of tidal streams as well, and we can also see that there's some spirals forming too, which is quite impressive. If we move over to the medium sim, this increases a lot more. I guess the general amount of warping is amped up quite a lot, which is what we'd expect. A higher mass satellite does create creates a lot more damage to the disk. And then if we have a look at the large sim, so that's 4 times 10 to the 10 solar masses, we can see that stars are getting strewn all over the place. It is absolute chaos. Everything is just warping like crazy, and then it all settles down later on. What's really interesting is that while it is difficult to put all of these videos on one screen and have you be able to see things really clearly, the time scales of everything to sort of scale down, quiet down, and return to some level of normal, which is very subjective in this case. The timescales for this are quite similar actually, which is really interesting. For contrast, here are the results of the control simulation. I know, super exciting, but it is important to have controls in here to see how the disk evolves in isolation and make sure nothing silly is going on. So the next set of videos I'm going to show you feature both the height of the stars above or below the disk plane, and then the vertical velocity of the stars, which basically is the same thing but in velocity, of course. There are 2 really interesting things that feature within these simulations that I wanted to discuss. So firstly, after the impact, you see the warping goes absolutely crazy. The stars reach really high vertical heights, and also vertical velocities as well, both up and down, which all dies down at roughly the similar time scales, you know, kind of similar stuff that we were seeing with the surface density, which is reassuring. Another interesting thing is that these warps are very highly corrugated and somewhat twisted in a way, so it's not like it's all going up in one smooth S-bend shape. It's like the warp has been twisted. Which is why it looks so corrugated, like it's going up and down, which I thought was really interesting. And the second thing is that you'll notice it's very difficult to sort of be able to point this out, but whatever the alignment is of the warp in the height, so that's on the left hand side, the velocity has a very similar pattern. However, it's been shifted by roughly around about 90 degrees, and that's going to be really useful in informing us what model we're going to use to then model the height and vertical velocity. But I'll save all of that for part 2, which will be up in a week. Thank you very much for watching me talk about my research. It was really fun to do, and I hope you learnt something new and really enjoyed watching all the pretty videos. Next week we're going to be looking at the data analysis a little bit further, more so focusing on fitting models to the height and the vertical velocity. Thank you very much for watching, and I shall see you next week. Don't forget to subscribe.